Welcome to our project, the autonomous Nerf gun turret. Our task was to create an autonomous Nerf gun turret capable of 360-degree motion, tracking of a target, face, or humanoid mass without user input by April 15th for under $500. This is ECE 4960, Senior Design 2, in the spring of 2024. Meet Team 9, Nerf or Nothing. We have John Carcott, Sam Buckley, Colby Till, Brandon Evans, and Foster Bolden. The objective/motivation for this project was to create a fun yet challenging senior design project. Choosing a Nerf blaster allowed us to upgrade and improve a toy that we all had as kids and allowed us to have some fun with this last senior design project we had. The goals and deliverables of this project was to create a fully autonomous Nerf turret capable of tracking and firing at targets, a face or humanoid mass, and to track 2 or more targets within 15 meters of the camera's view while moving. So this is the final prototype that we ended up creating. And as you can see, we have the Nerf blaster on top, and then all the hardware and computer is down below on a rotating base.
So this is our block diagram. We use a Pi 4B as our main controller, and then everything is controlled off of that with 5 motion detectors, a depth sensor camera, a servo, and a 12-volt DC motor, along with the Nerf gun itself. These are some of the hardware we use, like a 2S LiPo battery, along with buck converters, servos, Intel RealSense camera, the Raspberry Pi, along with motor drivers, infrared sensors, the 12-volt DC motor, and the Nerf Rival Nemesis blaster, along with a Google Coral USB accelerator. So our hardware design used a Lazy Susan track sandwiched between the 2 wood boards in order to create a frictionless movement. Those boards were cut out of 3/4-inch plywood, laser cut, and then we used aluminum extrusion to make a modular mounting system to the Nerf blaster. So we had 7 main components. We had a servo mount as listed number 1, which allowed the servo to attach to the frame. We had DC motor mount in the back, along with number 3 is our wheel, in order to create friction to allow rotation between plate 1 and 2. And then we used 5 PIR sensors placed evenly around the top plate in order to create a even coverage to prevent any dead zones. And then we used a custom made 3D printed mold in order to grab the Nerf gun securely. And then we had a camera mounted to where the sight normally was on the Nerf gun. And we used a 5mm steel axle in junction with the servo to allow a pivot point for the Nerf gun that allowed us to adjust the center of gravity so the servo would not have to do much work in order to adjust the aim. And then we converted the battery voltage to the 5-volt for the servo and the Raspberry Pi using a buck converter. And then we had positive and negative ground buses mounted to the frame.
So for the software of our project, our main controller was running Raspbian OS, the Bullseye version. This gave us numerous controlling abilities and also allowed us to use Bluetooth and Wi-Fi. So most of the program was created in C++, which runs our finite state machine, multi-threading capabilities, our controller inputs, also controls the hardware through the wiring Pi library, and also has data logging through the SPD log library, which helps us find errors inside the field. So we also have Python 3 for object detection, which runs the OpenCV library and TensorFlow library. So as you can see here, these are our states from the finite state machine. We start in the idle state in which motion is detected by the PIR sensors. It goes to the object detection state. And then to get to the warning state, the target just gets closer, and then get in the firing state, the target gets even closer. Once we get to the firing state, that's when we shoot the Nerf blaster. And then it just digresses with the same ideals.
So this slide shows the logic taking place during the object detection state. So during this state, the camera will capture an image, and that image will be ran through our model for detecting humanoid masses. It'll look for targets. If there are targets, then the pixel locations between the two shoulders of the target are determined, and then those points are then placed into shared memory. And then if the target is not then centered in the camera, then the lazy Susan will be rotated so that it will the target will be centered so that the gun will shoot at the target.
So our project has two different modes. We have the manual mode, which is where the user uses the controller, and we also have the autonomous mode. This flow diagram shows how when the user presses the minus button on the controller, it goes between the different modes. The autonomous mode runs the finite state machine, while the manual mode just lets the user control all of the motors and blaster controls. So talking about our methodology here, the finite state machine allows us to split our system into distinct states. This lets us do certain actions without having any other action take place. So when you're in the object detection state, you will not be shooting for no reason.
Then we also implemented multi-threading so that we were able to have instantaneous response from the controller. We used a depth camera to provide the distance of the objects so that we weren't shooting an object that was too far or out of range. While in autonomous mode, we also used artificial intelligence to detect humanoid objects from the camera feed. This was necessary as humans are complex objects and the camera feed wouldn't have a neutral background, so it was important to be able to accurately detect humans in the feed. And in order to do this, our Raspberry Pi 4 was too slow in terms of its inference times, so we used a TPU to speed up the inference times. We also used shared memory so that the C++ program and the Python program would be able to talk to each other and fire accurately.
So for our results, we were able to use a Bluetooth connected controller up to 25 feet. And this controller allowed for manual control, which let us aim and shoot. It also had a horn and a laser. Then we had the autonomous mode, worked very well, tracking just one person, but due to issues with distance sensing and speed with the camera, it had issues with multiple people. The main challenge was Bluetooth range, which we were able to solve by making a makeshift antenna with a Bluetooth connector USB. Our other main issue was battery life, as we don't have a large base, so our battery was limited and we only have about 30-40 minutes of active use. For the future, we want to develop a low power sleep mode, which would allow only the PIR sensors to be active until motion is detected, which would increase our battery life. We also want to upgrade the base, make it taller, and have wheels for easier mobility. We'd also improve the wiring so it looks nicer and is cleaner. In conclusion, we were able to successfully upgrade Nerf Blaster to be more powerful, while allowing it to be controlled by a wireless controller and autonomously. And these are our references. Thank you.
It should get you about the time you clear the table. 4. What did you change it to? You're in like 8 or 9 right in the corner. Try me, punk.